Today's vocabulary video notes are for in-class 77. This is part 1 of standard 18, and we are going to be learning about tangents today. In order to deal with tangents, we're going to have some algebra skills pop back in that we haven't used for a while, which is why these notes begin with some algebra review. Our goal is going to be to simplify expressions that look like something squared in some of these cases. So if we think back to what squaring means, we take the expression and we multiply it by itself. That's what it means to square, or when we have an exponent of 2. If you think back to the process, we have a lot of distributing to do in order to multiply these two binomials together. X is going to multiply by x, which will give us x squared, x times x squared. X will also multiply by positive 8, giving us a plus 8x. And then positive 8 will multiply by x to give us another positive 8x. And last but not least, positive 8 times positive 8 is positive 64, so plus 64. That is not the same as just squaring x and squaring 8. That would only give us this first term and this last term, and we would miss out on these two middle terms, which can combine together to be a 16x. So when you square, you cannot use a shortcut where you just apply the exponent to the two parts of the expression. You need to multiply the expression by itself and do all of the distributing required to multiply those two binomials together. After that, we combine the like terms. We leave anything that's not a like term. X squared doesn't match anything because it has a different exponent. 64 doesn't match anything else because it's a constant. And so our simplified or expanded expression would be x squared plus 16x plus 64. Go ahead and pause the video and try the second example on your own. And then when you restart the video, I'll walk you through it. Okay, we are squaring. So we need to do 3x minus 5 times 3x minus 5. 3x times 3x is going to be a 9x squared. 3x times negative 5 would be negative 15x, so that will look like minus 15x, subtraction. Negative 5 times 3x will be another negative 15x. And negative 5 times negative 5 will be positive 25. Again, we have some like terms in the middle. So 9x squared stays on its own, but a negative 15x minus 15 more x's would be negative 30x total, plus 25 to finish it out. We'll see in the examples that we do in class tomorrow why that algebra skill is important to remember. All right, so today's focus, as I said, is tangents. So a tangent is a line, a segment, or a ray that intersects a circle at exactly one point. We've talked about tangents before when we were dealing with angles that were inside, on, or outside circles, but now we're looking at tangents and in terms of their segment lengths, usually. And there are a couple of theorems related to what's true when a tangent intersects the circle. So let's look at theorem number 1. A tangent to a circle is always going to be perpendicular to radii of the circle. Just as a reminder, perpendicular means that it's going to form a right angle. And then we learned a while ago that symbol for perpendicular was that upside down T, where we see those right angles in the corner of that symbol. And so in this diagram, we already have a tangent drawn. So this would be the point of tangency, the place where that tangent intersects the circle. So if I go to the center of the circle and I connect to that point of tangency, that is a radius. And that radius, according to the theorem, is going to be perpendicular to that tangent. And so a right angle can show up anywhere a tangent and a radius intersect. Now, if you think about a diameter, it's actually two radii put together. So the same thing would be true if a diameter and a tangent intersect. And then what will happen is we'll have triangles connected to this, and we'll use some of our previous standards with our triangle information to solve problems. So you might have c squared equals a squared plus b squared, Pythagorean theorem on your radar. You might be using trigonometry, SOHCAHTOA, or you might be using your special triangles, 30, 60, 90s, and 45, 45, 90s. So we'll see examples of those three things when you're back in class tomorrow. Tangent theorem number 2 is talking about tangents that are to a circle. So we've got these two rays that are both tangent to the circle from a common external point. So right here, those tangents originate or pass through a common external point, a point outside the circle. And so what happens in this case, if we kind of draw in a quick picture here, we connect that common external point to the center, and then we connect to those tangent with radii. We just learned that these will be right angles, and we know that all radii are congruent. And then we have this segment in the middle that's shared by these two triangles. And so then all of a sudden, we're back in first semester where these two triangles are congruent by HL theorem. It's been a long time since we've looked at some of these first semester pieces of information, but they're all still true. And so what happens if these two triangles are congruent by HL theorem is that these tangent segments out here are going to be congruent as well. That's actually CP/CTC in action. Corresponding parts of congruent triangles are congruent. Now, because we have this theorem, we don't have to go through that process every single time of looking for those congruent triangles, explaining that they're congruent because of HL, and then using CP/CTC. If we see the situation where we have a common external point and then we have tangents to the same circle from that point, we can go ahead and automatically add in these congruent marks and use that to solve problems. All right, that's it for your vocabulary notes for today. Bring those back tomorrow and we will do examples where we'll practice applying that information.